Chapter 9, Section 1, we're looking at how you can prove the Pythagorean Theorem. Okay, so we're looking at the Pythagorean Theorem. Starting off, we have the Pythagorean Theorem. In a right triangle, the square of the length of the hypotenuse is equal to the sum of the squares of the lengths of the legs. And so we have legs of A and B, hypotenuse of C. Our book writes it as C squared equals A squared plus B squared. It's more commonly seen as A squared plus B squared equals C squared. It's just flipping where things are on the equal side, so that is our symmetric property and fine. Example 1, find the length of the hypotenuse of the right triangle. Hypotenuse is always opposite the 90 degrees. It's also always along the side. So we're setting this up here. We have 7 squared plus 24 squared equals x squared. So 49, 24 squared is 576 equals x squared. I'm going to add these together. 625 equals x squared. And then take the square root of that. So the square root of 625 gives us that x is 25. Example 2, a 6 feet board rests under a doorknob and the base of the board is 5 feet away from the bottom of the door. Approximately how high above the ground is the doorknob? One thing to think about here is where things are, right? So a 6 foot board rests under the doorknob and the base of the board is 5 feet away from the bottom. So the base of the board is 5 feet away. We're looking for the height. So our board comes up this way and that is our 6 foot board. Okay, resting under the doorknob. So here, I realize a lot of people make the mistake of always putting the variable where C is. That's not the case. Here the variable is either A or B. It doesn't matter which one you make it, but it's one of the legs. So I have h squared plus 5 squared equals 6 squared. So h squared plus 25 equals 36. Subtract the 25 from both sides. I have h squared equals 11. So h is the square root of 11. Watch what the directions are saying. In this case, they don't tell us anything. So the square root of 11, which is simplest radical form, or 3.32 feet, both are acceptable. If it says simplest radical form, you have to have square root 11. Example 3, find the area of the isosceles triangle with side lengths 16, 17, and 17. So first, remember that area of a triangle is 1/2 base times height. So I need to know those measurements, and that's where the Pythagorean Theorem is going to come in. We have side lengths of 17 and 17, a base of 16. So when our height comes down here, it's going to cut that side in half, and I'll have a right triangle with 17, 8, and our base, or our height, is the other side. So I'm doing 8 squared plus h squared equals 17 squared. 64 plus h squared equals 289. Subtract the 64, h squared is 225. So my height is 15. So when I'm plugging in here, I have 1/2. Now watch, my base is not the 8, it's 16. And my height is the 15. So I multiply that out and I have an area of 120 meters squared. Example 4, find the unknown side length. They give me this is 11, and they have things marked equal here. So I have x is my hypotenuse, so I have 11 squared plus 11 squared equals x squared. This is one where simplest radical form can be helpful. I have 11 squared twice, so my final answer is going to be 11 root 2, which is something you could use, but if you work through it, get 121 plus 121, which is 242, equals x squared. Take the square root of that, and as I mentioned, you have 11 root 2 equals x, and that's approximately 15.56. Okay, then underneath that we have common Pythagorean triples. These are numbers where they always work on Pythagorean theorem, and they're always whole numbers, and the multiples work. So 3, 4, 5 works. Times that by 2, you get 6, 8, 10. Times that by 2, you get 9, 12, 15. If I times it by 10, I'd have 30, 40, and 50. Right? So they give you some examples here. Technically, anything that has 3 whole numbers and works is a Pythagorean triple. Especially the 3, 4, 5 and the 5, 12, 13. That and multiples you see a lot on standardized testing, and it can make life a lot quicker. If you see that I have sides of a hypotenuse of 15 and a leg of 12, I can just say, okay, I'm doing 5 times 3, 4 times 3, so 3 times 3 is 9. It can save a lot of time. That would be the advantage of knowing the Pythagorean triples. Then we're looking at the converse of our Pythagorean theorem. Okay, so we're going the opposite direction here. This says if the squares of the lengths of the longest side of a triangle is equal to the sum of the squares of the lengths of the other 2 sides, then the triangle is a right triangle. So let me check and see if something is right. So the longest side is always going to be your C in this case. So on example 5a, I have 24 squared plus 16 squared, and I'm comparing that to 29 squared. So 24 squared is 576. 16 squared is 256. And 29 squared is 841. So I have 832, which is not equal to 841. So this is not a right triangle. Okay. If I look at B, I have 6, 9, and 12. Okay. So 6 squared plus 9 squared compared to 12 squared. We have a 36 plus 81 compared to 144, right? And 117 is not equal to 144, so this is not a right triangle. Okay, if these two were equal, that would be a right triangle, and that's somewhat useful, but not as useful as we'd like. So we get into the next thing here. What type of triangle is it? So now again, they flip the order here in the book. You look at it either way. If c squared is equal to a squared plus b squared, it is a right triangle. That's what our Pythagorean theorem says. If a squared plus b squared is bigger than c squared, which is 2, c squared is less than a squared plus b squared, then it is an acute triangle. Okay, so which doesn't apply to either of the ones we looked at. If I had something like here, if this was 852 instead of 832, 852 is bigger than 841, that would be acute. Okay, if c squared is bigger than a squared plus b squared, and c is less than a plus b, it's obtuse. Otherwise, it is not possible. Okay, and this goes back to when we looked at 3 sides of a triangle, any two had to add up to be greater than a third. So here 24 plus 16 is bigger than 24. This is obtuse. 6 plus 9 is bigger than 12. That is obtuse. Okay. So then example 4, the side of the segments form a triangle. If so, would you say it's acute, right, or obtuse? Right. So 10 plus 15 equals 25. That is not possible. Right? They have to add up to be bigger. When I look here, realize they're not always in order. 8 is the biggest. That's my C. So 4 plus 6 is bigger than that. So I do 4 squared plus 6 squared compared to 8 squared. I have 16 plus 36 compared to 64. So that gives me 52, which is less than 64. So this is obtuse. Right here, 11 and 10 is bigger than 14. So 10 squared plus 11 squared compared to 14 squared. 100 plus 121 compared to 196. This is going to be larger, so this is acute. Example 7, 3, 4, 5. That's our triple, so you can do the math there. That's going to be a right triangle. Right. B, if I'm giving you one like this, I would have them in the right order, so you don't need to figure out where 3 root 2 goes in there. 3 root 2 is actually smaller than 8. So 3 root 2, I'm squaring the whole thing, plus 6 squared compared to 8 squared. So 3 root 2 squared is 18 plus 36 compared to 64. This is obtuse. That's how we use Pythagorean theorem to not only solve for sides of our triangle, but also see if our triangle is right, acute, or obtuse.